Might sound a little bit boring, but I promise you it's going to get pretty sweet pretty quick. We're going to start off right out the gate with this stuff in here called liquid nitrogen. Now, this is like a giant thermos. It keeps really cold things cold and really hot things hot. So, we're going to get some of the contents of this liquid nitrogen into our beaker right here. So, you're going to see when I pour it, creates a fog. Well, that fog is because this liquid nitrogen is extremely cold. All right, there we go. And if you look closely, Keisha's brought in our close up camera. You're going to be able to see that this stuff is boiling. Now, I just said it was cold, right? It's kind of weird to think of something boiling being really cold. Well, water boils at 212 degrees Fahrenheit. Nitrogen, that's what this is, boils at negative 321 degrees Fahrenheit. Negative 321 degrees Fahrenheit. So this boils 500 degrees or more colder than what water will boil at. So that's a big difference. So when we think about what this stuff is doing, it is warming up right now. Yeah, I can actually feel it around the outside. It is extremely cold. This stuff is so cold that it changes the way some things behave. So we're going to be looking at that. And you saw I was shooting this rubber band earlier today, and I was so stoked. I got it in the container. It only happens about once every 100 tries or so. And we're going to see how the nitrogen, being extremely cold, changes the way that the polymers in this rubber band work. So these rubber bands have chains in them, chains of molecules that can coil up and uncoil and coil up. Well, is it going to do that when it's really cold? I wonder. Let's drop it in, and we're going to see. Woo! It's going to be very cold in there. You're going to see some extra bubbles because the room temperature rubber band went inside and started cooling off. And as a result, it warmed up the nitrogen just a little bit. Let's get it out, and I'm going to give it a little squeeze. Ooh, look at that. We shattered it. So this rubber band became rigid, and it started, instead of bending and flexing and moving, it just broke. Now I'm going to warm it up with my hands until I can feel it kind of getting back to the way it was before. There we are now. And check it out. A stretchy rubber band again. Ow. We're going to try that one more time just to make sure that this is consistent. So we have our stretchy rubber band. Ooh, can I go for the 2 in a row? Am I going to make my own trick shot channel? Nope, not at all. Whoa, that's kind of cool. The static made it stick to the side of the table. That's awesome. Side experiment. That's not part of the script. That's just like a cool thing that happened. So we're going to do this one more time. Shake off the nitrogen. Give it a nice little shatter. Isn't that awesome? So you can see that piece and you can see some of the fog coming off of it. It's all rigid, and slowly it's going to start warming back up. Now, while Keisha shows you that, I'm going to get out a second item. Oh, wait, I need to use a different color. We'll go green. So I've got a balloon. What do we think will happen when we put an inflated balloon inside here? So I'm going to inflate it up. And so I made a animal for you guys before. I made a little seal. It was supposed to be a dog, but the nose exploded. So I turned it into a seal. I'll make a second animal. So what I need you to do is in the chat, or not, excuse me, not in the chat, on your screen, I need you to show us like what do you want it to? Do you want it to be a little rabbit? Do you want it to be like a how do you do a fish? Like a fish? What do you want it to be? Keisha's gonna take a look, see what we get. I have an idea of what I want to do, but I want to see if you guys have anything clever. Ooh, snake. I think I can. I think I can pull off a snake. Yeah, let's go with that. I love it, Keisha. Boy, that person made my life easy today. Thank you for choosing a snake. I got it right out the gate. That's just about it. Here we go. All right, so let's get our seal and our snake, and we're gonna dunk them in nitrogen. What do we think is gonna happen? Talk to your neighbor if you're in class. Talk to your bedpost or your bunny or your pet cat if you're at home. What do you think is going to happen? So we saw with our rubber band that it shattered. Do we think that these are going to shatter? This is made out of a little bit of a different material. This is a latex material. The other one was a rubber band. Is it going to immediately pop? Is it going to crack? Let's find out. Let's start with our snake. There we go. And we're going to just kind of dunk them head first in here. You may not be able to see it right now, but this is actually starting to deflate. Now, that's actually a little bit of a misleading term. While we say deflating, what's actually happening down in here is all of the air that was inside that balloon has condensed into a liquid. So the gas molecules are energetic and they're flying all over the place like kindergartners at recess after drinking a Coke. They're just bouncing off the walls. And then when they cool off, when molecules cool off, they slow down. A little bit more around your pace. They slow down and they take up less space. So the molecules inside that balloon are taking up less space right now, but it's still the same stuff. So we inflated this with an air pump, so I didn't use my breath. So the contents of these little pockets is just atmosphere, it's just regular air. So that's going to be mostly nitrogen gas with a bit of oxygen in there as well. So when we think about it, this is made up out of gaseous nitrogen and oxygen. This liquid nitrogen is cold enough that it can condense the air in here into a liquid. We're going to test it out on our little seal. There we go. Down it goes. You see it starts to shrivel and wrinkle and get down. There it goes. All right, so we have that part of the experiment done, but we still need to take our animals out. What do we think our guess is going to be when it comes out? Is it going to reinflate? Is it going to pop? Is it going to stay like this? I wonder. You guys want to check it out? You want to find out? I sure do. Here we go. Let's take out our seal first. There we go. And then behind it, we'll put our snake. And if you look, it's beginning to grow. Isn't that weird? Whoa! That snake wanted to attack me. That's pretty cool. So this one, the balloon like had a little crack or a little split somewhere in it, so the gas was able to come out. But it looks like our don't sit on that hot thing. That would not be good. But it looks like our seal was able to survive. It's wow, that was loud. Oh man. I don't know why that was so loud, but that was insanely loud. Boy, check that out. So we popped one leg, but man, my ears are ringing, Keesha. What about you? That was intense. Yeah. Sorry guys, we may have damaged our eardrums just a touch. Yeah. Wow, I actually haven't really seen that happen before where just one leg like pops. So not only did I get a rubber band in the container, but we also had a one of a kind eardrum damaging experience. That's fantastic. So science that's live. So if you as you can see, the liquid that was in here when it was down in here, remember it was all condensed and wrinkly. Once we brought it back out to the table, the room temperature started raising the temperature inside here higher than the threshold for the oxygen and nitrogen to stay as a liquid. So it boiled back. Well, these things are all kinds of weird today. So it boiled back into a gas. I think I need to get rid of these. These might be slightly possessed. So see ya. We're going to do another experiment with one that's a little bit slightly more predictable, I hope. But based on how this program's going, who knows what's going to happen. So this is a playpen ball. So I wonder, how is this going to behave differently or the same compared to a balloon? So with our first one, we had the rubber band. It got really hard and it shattered. With the second one, man, my ear still hurts. The second one, with that balloon, it got really small. It took up less space. Well, this one is made out of plastic. So these are designed to handle children jumping on them over and over and over and over. So when you go to a ball pit, you like jump and you face plant and you smash your face into this over and over and over, and these things can survive. They're filled with air, and that air is sealed inside, so it creates like a kind of a soft plastic cushion for you to land on that hopefully keeps everybody safe in the ball pit. Uh, so what do we think is going to happen when we put it in our nitrogen? Is it going to cause the plastic to just shatter? Is it going to condense down like what we saw with our balloon? I'm curious. Talk to your neighbor at school. Talk to your bedpost or your kitty or your dog or your goldfish or your plant and say, I think the playpen ball is going to, and create your hypothesis. What do you think that's going to do? I want to find out. So we're going to have to test this. So we're going to place it down in the nitrogen. You're going to be able to see the nitrogen boil all around it. It gets nice and cold. There we go. Oh man. And by the way, this one is going to make a little bit of a pop. So just give you a little bit of a heads up if I exploded your speakers here a few minutes ago. Now, the other thing I need to do is I need to put on a glove for this one because I'm actually going to hold it in my hand for a couple seconds. So I can show you the ball is still intact. We're going to dunk it one last time, and we're going to pull it out, and I'm going to give it a whack with these metal tongs. Here we go. Check that out. How cool is that? It caused it to shatter, and if I'm not sure if you could hear it all that well over the sound system, but it made a really loud popping noise on our end. And the reason it made a loud popping noise was that, remember, it was the same size inside here? Well, that plastic became really hard, and so it kept its shape. So, like our balloons, for example, the latex of that balloon kind of shrunk down. The latex still moved. Well, this did not want to move. The plastic did not want to move, so it kept its shape. But let's think about what was happening to the gas inside of it. Well, the gas was condensing. And remember, when gas condenses, it takes up less space. So we have a little bit of a paradox to think about. With this sphere, we had gas condensing down to a liquid and taking up less space, but the space was the same size, right? So this ball was still the same size, but the liquid was taking up less space compared to when it was a gas. Well, the result is a vacuum. So there was a vacuum inside this ball. There was no air. It was liquid and then basically space, like outer space. There was no stuff inside of it besides that liquid. So when I hit it with this, it took a couple whacks, but by the time I hit it that second time, it cracked it and air rushed inside. And as air rushed inside, it made a really loud popping noise, and you could hear that boom, and then it shattered. As the air rushed in, it just shattered this thing into dozens and dozens of pieces, which is really neat. So that's a couple of demonstrations with our liquid nitrogen on different types of rubbers, latex, and plastics, especially looking at air. Now, this next one, I want to focus even more on the air by having a little snack. What I've got are some delicious Cheetos. This is the puff variety. So Cheeto Puffs are a little bit bigger than a regular Cheeto, and if you've ever crunched into one of these delicious bad boys, they have a lot of air inside of them. And so all these little pockets of air are going to be cooled off with our nitrogen. So let's find a good one. Ah, yes, that's it right there. So we're going to drop this down into the nitrogen, let it start getting really, really cold, and I actually am going to eat it. I do not recommend you eat frozen Cheetos at home. They are not quite as good as room temperature Cheetos. But for the sake of science, I will show you this one. There we go. Getting it nice and cold. So that's kind of what it looks like. We're going to shake out the last little bit of our nitrogen. I'm going to set it there for about 4 seconds. And then Keisha's going to back up as I take my mask down and eat a frozen Cheeto. Mmm. Mm. That's so it's like so good. Like, it's so delicious. A little bit frozen, but just as delicious of a Cheeto as ever. Oh, I love it. Now, let's talk about why we're able to see that really cool fog coming out of my mouth and coming out of my nose. Well, the main reason was because that Cheeto was so cold, it cooled off the warm, moist air in my lungs. I can show you that in another way. Take a look here. So, in that demonstration, just like with the Cheeto, when I blow my cold or my warm, moist air over this cold nitrogen, it cools it down into a fog. Just like if you've walked outside this morning, it is really cold. And so that cold air cools down our warm, moist air into that fog that we can see. Now, the last thing I'm going to do with this nitrogen for the time being is something called the Leidenfrost effect. And this last demonstration is actually going to show you how quickly this stuff, this nitrogen, will boil when it touches another solid. So right now, all it's really touching is the air up here, and it's touching the solid down here. So, and one other cool thing to look at is we've developed some snow on the outside of our container. How's that song go? Let it snow, let it snow. Can't bundle up in the cold anymore. Oh, there it is right there. Let's get all that snow falling down. And Keisha's going to go back a little ways, and I'm going to show you the lighting frost effect, where this nitrogen is going to hit this ground. When it hits the floor, it's going to start boiling because the floor is 70 degrees Fahrenheit, which is almost 400 degrees warmer than this really cold liquid nitrogen. So when it hits the floor, it starts boiling. When it boils, it actually lifts up on a little cloud of air. Let's take a look. I'll show you this a couple times. Wasn't that sweet? Yeah, let's take a look again. So those little beads of nitrogen floating around. You'll see it as a liquid, but it's skating on its own layer of air. And there's the last of it. How cool is that? So we're going to set our nitrogen aside because the next portion of this program is focusing more on how air moves around this room than the actual nitrogen itself. So let me show you what we've got right here. This container has air at the top and liquid at the bottom. So we're going to be exploring how the air and the liquid move past each other. This is called fluid dynamics. Now, what fluid dynamics means is when fluids, which can be liquids, gases, or plasmas, when fluids move past one another. So these molecules, like especially liquids, you can see it really well, they'll take the shape of their container. Well, gases do that also, but it's usually harder to see. So what we're going to do is we're going to flip this over, and we're going to look. This liquid is denser than this gas, so it wants to go down. But if you take a look, we have a very narrow channel for it to move through. So the liquid going down has to take turns with the bubbles coming up. Because as this goes down, you also have to remember this gas has to go up. They won't both go in there because then there'd be a vacuum in here, and that's just not going to work under these pressures. But we can speed up this process. What I can do is I can create a spiraling fluid. Think about when you drain your bath or a younger sibling's bath. What is that shape of that funnel going down into the drain? Well, it's a tornado. So let's see if we can create one here. There it is. There's our tornado. So interestingly, a tornado, also known as a vortex, is the most efficient way for fluids to move past each other, just like here. So that spiraling fluid is a very efficient way for these two fluids, even though this is a liquid and this is a gas, for these two fluids to swap places. The liquid's on the outside and the gas comes up through the center of the tornado, the vortex. And here at the Museum of Discovery, we like to take things up a notch. So what I'm going to do is get our slightly larger version of the experiment. So let's see if we can get it working with this Mondo version. Okay, there we go. Hard part's done. Now, same thing. It's going to bubble, 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 but I'm going to start spinning this top one and then hold it still. Ooh, we're almost there. There it is. Ooh, this is a pretty one. So you can see our fluid is on the outside. Our gas is coming back up through the inside. So you can even see the fluid on the outside here. But I love looking at how that tornado forms. Now, this vortex can be seen in nature. You can see it in a whirlpool if you have a body of water draining. If you've ever been canoeing and you pull the paddle through the water, you'll see that tornado, that vortex chase the paddle. You can see it in nature with, well, a tornado, right? And that's when hot air and cold air causes a shear force, and that shear causes a twist, and then you get that spin. You can also see it with a hurricane. That's like a big, giant vortex. So this is when fluids move past one another. What I want to do is show you another vortex, but it's a little bit different. So it's going to, you know how your tornado's like this? Imagine taking the top and the bottom and connecting them together. So we're going to create something a little different looking. Who? By putting this over here and grabbing what we call our airzuka. So we're going to come over to this big green sheet. We're going to take a look at how we're going to create a little puff of air that shoots out of this. This has a rubber band in it that when I pull it back, see how it fills up with more air? The rubber band is going to cause it to snap forward. See that? Isn't that kind of neat? So it shoots a puff of air out, and you can see it hit our tablecloth. All right? And I can turn around and hit Keesha. Her hair just like puffed out to the side. Can't really like see it with mine, but it's too short. But you can see it on that tablecloth. Now you can do a homemade version with like a box. You can just like cut a hole on the end of a box and then seal up all the rest of the box. And when you slap the sides, it'll shoot a puff of air out. You can fold little pieces of paper up and knock the paper over. It's pretty cool. Another way you can do it is with this thing, a giant trash can. This one takes a little bit more resource because you have to sacrifice a big hole in the bottom. So it doesn't become a very useful trash can after this. But you need some sort of a membrane on the top. This, imagine it like a drum, right? You can squish it in. And what we're going to do is the exact same thing with that airzuka. This is just like a bigger version of it. And if you look really closely, you can see that it's actually like a circle that's hitting the wall. Can y'all see that? You can kind of see it down at the bottom. See how that's a circle? It's partially because this is a circle shape, but even if this were cut out as a square, it would still come out, the puff of air would come out as a circle. Now, in order for you to see that a little bit better, I'm going to step away for a moment and I'm going to get some fog. Now, the way I'm going to get some fog is with like a theater fog machine. So I'm just going to fill it up over here. We're going to add some fog and you're going to get to see the actual shape of what these puffs of air look like. Ooh, I've got it. I've got it. Here we go. So let's take a look at what these puffs of air are actually doing. Here we go. Cool. I can try and hit it with a faster one. So I'm going to shoot a slow moving one, then hit it with a faster one. Oop, just missed it. So these rings are a tornado or a vortex, but looped on itself. And I'm going to try and hit a real slow moving one. And if you look really closely, you can see it flipping inside out over and over and over. So sometimes if you have long socks and you roll them up down your leg, that's kind of what these are doing. They're kind of rolling in on side of themselves. And this is we actually call the shape a toroid, but you can kind of think of it like a Cheerio or a donut. That's the actual shape of it, but it's flipping itself inside out. And that's how we're able to move this little puff of air all the way across the room, right? Normally, if I were to try and like blow, I'm not going to do it right now because I don't want to take my mask down and blow really hard. But if I were to try and move that sheet, it'd be really hard to do it with my breath, with my lung power. But with this thing, no problem. I can hit it like really far away, right? I can hit it from like all the way across the room. I could go even farther than that if I had more space. So with this vortex generator, you can create these toroids, these rings, and you can see just how efficiently those spiraling fluids move throughout the room. It's really neat looking. Let's get Keesha one last time. Got her. All right. Now I want to bring it toward our grand finale, which kind of combines everything all at once, and then we'll be able to answer your questions. So remember, if you want to answer a question, fill out that Google form. I believe you can access it through your Schoology app. So we're going to start working toward our grand finale, where we're going to get to see a little bit of a vortex, as well as go back to some of our really cool liquid nitrogen. So we're going to combine some hot water. I'm going to put some really hot water in here, and we're going to put some nitrogen in here. And when we combine the two, well, that nitrogen is going to warm up very quickly. We're going to see a lot of fog, and it's going to create a little bit of a vortex coming out of this. We have a teacup or a metal pitcher inside here with a restricted neck. So it's going to shoot a vortex out. I want you to watch for that when we hit it with our hot water. So let's start getting that ready. Here we go. Here's the nitrogen. Don't forget to ask your question in the Google form because we're getting pretty close to when we're finishing our program. Let's see. I think we're getting about ready. It is time for our nitrogen. Yeah, it should be good. And next up, hot water. Now we're using equal proportions of hot water and nitrogen. I'm going to go a little bit heavier on the water this time. Just a little bit more water than nitrogen. I'm going to put my gloves on. And to see this grand finale, I need you all to help me count down. Oh, got my mask all flipped around. I need you to give me a countdown starting at 5, 4, 3, 2, 1. Woohoo! All right. There it is. And I may have splashed Keesha with a little bit of water. And that's what happened. We had that hot water go inside, mix with our nitrogen. It quickly warmed up that nitrogen, caused it to take up a lot more space. So remember when our balloons went from a liquid when it was condensed and then they on the table warmed back up and they took up more space? Well, the nitrogen that was inside here warmed up and took up a lot more space, and it shot that vortex up to the ceiling, and we even got the ceiling a little bit wet because that was a really cool eruption. Now all of our nitrogen is gone. All we have left is this really cool looking fog. Isn't that neat? All right, we are just about towards the finish of our program. So Miss Barnes is going to take a look at that Google form, and she's going to see what questions you guys have developed so that we can answer What's on your mind? So, Miss Barnes, whenever you are ready, let's see what our first question is. I know it might take a minute to get some of those questions in. Keisha, let's make sure that Miss Barnes is able to unmute herself. I hope we didn't disable that for her.
She is a co-host, so
Oh, okay.
she's good.
Okay, okay. I am just getting one. I have one so far. And it is I wonder what would happen if you put a balloon inside boiling water at 260 degrees Fahrenheit.
Hmm. That's a good question. Let me think about it for a moment.
That's a question.
So, I have a guess, but I haven't tested this, so I really don't know. Um, but it makes me think, I think two things might happen. So, one, it's going to relax the latex. So, as you get that latex hotter, it's going to relax. It might get so relaxed that it ruptures. So, it might pop in the boiling water. The other thing that I think would happen is that that gas that's inside the balloon, well, that's going to heat up too, right? And the more you heat up air, the more space it takes up. So when you think about like a hot air balloon, all it's doing is it's heating up the air and it takes up more space and it becomes less dense. And that's why hot air balloons lift up because it's less dense than the air all around it. So it lifts up. So I don't think that the balloon would lift up. I don't think it would have that wouldn't happen, but or wouldn't likely happen. But I think it would expand. I think it would like actually like get a little bit bigger. Um,
That'd be
but I
cool.
know for sure it would increase the pressure, or I don't know for sure, but my hypothesis that it would increase the pressure inside the balloon, and the latex would be getting more relaxed. So my guess is there might be a decent chance it would pop. That's that's my guess. I think it would probably pop. It's a really good question. I like the way you're thinking about. All right, well, that's what happened when we got it really cold. What would happen if we got it really hot? I like it. Let's see if we have a second question from some of the
Yes.
students.
Why did the liquid nitrogen turn into ice when it touched the boiling hot water?
Ooh, yeah, that's a good one. So over here, I had liquid nitrogen in the bottom, and then I added boiling hot water, and you saw that fog shoot up into the air, and you saw that kind of vortex that we were talking about, that ring. It was it was very quick, but it was there for just a moment, and you had this column of fog. So that fog was the same reason we saw fog when I blew down into the nitrogen and saw the fog come out of it. Same reason we saw the fog when I had the Cheeto in my mouth. So whenever you cool down warm, moist air, it creates that fog. Well, boiling water has a lot of there's a lot of heat, and it has a lot of moisture. So you can create a lot of fog from that. Um, and then on this one, I had a little bit more water than in the previous demonstration. So we didn't end up with as much ice down in the bottom of this. But what you do end up with at the end of that demonstration is there will be ice down at the bottom because the water that we dumped in went from 212 degrees all the way down below 32 degrees. So it started freezing as well. So that's why we had, because the nitrogen was so cold that it brought that temperature all the way down to where the liquid would turn into a solid. Excellent question.
Okay, I may need this question is from Brady. Brady, you may have to help me with this one. It says, what would happen if it was your breath because it's carbon dioxide? So Thomas, if you don't understand that, we'll get
I
Brady
know
to.
exactly what he's thinking.
Okay.
So this is a really cool question, and so he's thinking dry ice. So if you've ever been in our FizzBoom Science dry ice lab, we experiment with frozen carbon dioxide. And I think I know where he's thinking. So he's like, all right, well, we breathe out carbon dioxide. And when carbon dioxide gets really cold, it turns into a solid called dry ice. So did I create any dry ice when I breathed down into the liquid nitrogen? The answer is yes, I did. It's going to turn into a dry ice powder. So basically, dry ice snow. The way I have seen that in the past. So if you notice, like I used this device to inflate the balloon. So that means it had atmospheric air inside of it, which is mostly nitrogen and a bit of oxygen, about 78% and like 20%. So the balloon didn't have very much carbon dioxide in it. Now, in the past, I have filled up balloons with my breath, which has a lot more carbon dioxide in it. Still has a lot of nitrogen, still has a lot of oxygen, but there's more carbon dioxide in it than if we use this. And I have actually seen when I've blown up balloons in the past and put them in the nitrogen, when I've pulled them out, if I use a clear enough balloon, I have been able to see small flakes of dry ice bouncing around in there. So, yes, we can create dry ice more like carbon dioxide snow than like dry ice. That's when they kind of like pack it down and it's like really solid. But the theory is all there. We do create dry ice when we breathe into something cold enough to take the carbon dioxide gas down into a solid. Now, this is something weird to think about. When you think about our nitrogen exists at a liquid phase much colder than dry ice. Dry ice will turn into a solid at negative 109 degrees Fahrenheit. So nitrogen is almost 3 times colder, but it's still in a liquid phase. Nitrogen has to be, I believe it's around negative 380 degrees Fahrenheit for it to turn into a solid. So it has to be way, 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 way cold for it to turn into a solid. Carbon dioxide, it just has different properties. And so it will turn into a solid at negative 109 degrees. And carbon dioxide will only exist as a liquid under really high pressure. So it has to be contained in a big metal container. And that's actually what they use in restaurants to like fill up soda machines. They use liquid carbon dioxide. So I think that's kind of where Brady was going with this question. But yes, we can and have created dry ice snow with our breath when breathing onto liquid nitrogen.
Okay, we don't have any other questions at this time. We have a few more minutes. Does anybody have a question that you want to submit really quickly? No other questions? Okay, I just knew Tyler would have a question today.
They're just so awestruck. I mean, how can they possibly type after seeing something so cool as that? But yeah,
Uh,
if we're done with questions, I just wanted to say thank you guys for joining us. I know this is a little bit of a different format. We certainly want to be in person to show you that incredible spectacle up close, but we want to be as safe and hygienic as we can. And this is a great way for us to be able to connect to you guys. We hope we get to do some of our other programs with you virtually or in person, maybe down the road. So we really appreciate y'all tuning in from home and from school. And if you have any questions, just let Miss Barnes know. She can email us, and I'll answer them to the best of my ability. I like those questions that I heard earlier. It's really neat to see how you guys are thinking about some of what we've experimented with and how it applies to other parts of life. So thank you guys. Let's give Keesha a round of applause for running the studio so well. Excellent job, Miss Keesha.
you guys,
And I hope you guys have a great
unmute
day.
yourselves. Am I muted? Unmute
No, you're not
yourselves
muted.
and
No,
give,
you're not unmuted. I mean,
unmute yourselves and give the speaker a round of applause, please.
Okay. Thank you.
Okay, that's good. That's enough. Thank you.
All button comes in.
appreciated being with you today. Have a good day, guys.
Thank
Bye, y'all.
you.
Bye.
Bye.